Let's use the Hall-White one-factor model as an example to illustrate how we can build a trinomial tree. Because trinomial trees gives us more flexibility, and here, when we build an interest rate model, we really have we need to handle the mean reversion, and also we want to match the initial term structure of interest rate. So to let's see how we can utilize a trinomial tree to achieve both of those desirable features. Now, if we follow the approach taken by Hall-White, the tree is actually built in 2 steps. The first step is we actually build a relatively standard tree, and once we have built that basic tree structure, then we make adjustment to the tree to match initial term structure of interest rate. Okay, that therefore we then have an interest rate process that matches the initial term structure of interest rate. Then we can price the options based on that interest rate tree, and we know with that structure of interest rate tree, the initial term structure of interest rate is actually matches perfectly with what we observed currently in the market. In the first step of building the tree, essentially we're building this part. So if you see, this is theta times dt and minus AR times dt. So we will ignore this theta part. We just basically have this minus A times R dt plus sigma dz. That's basically what we built to begin with. So let's define, say, a different variable, the big R star, and then this R becomes R star. Because the reason we have to use a different one is because this little r and the big R star, two different have different values, right? And then once we convert it back by adding this adjustment factor, we then get the little r that we need. So to begin with, we set the initial value of the R star to be 0. So it's start at a 0 point and then just expand it. Okay. Let's see. So according to their research, Hall and White basically said, what is the optimal step for changing interest rate? They said, well, the best way for numerical efficiency is to do that at the at the step of delta R as equal to sigma times square root of 3 times delta t, okay, as the step for delta R. So if you have R is 0 here, then this is delta R up, this is minus delta R, okay, and but the distance is this sigma times square root of 3 times delta t. Because it's a trinomial tree, we have 3 probabilities. So we have a probability of moving up, and a probability of moving down, and also a probability of unchanged. Okay, and so we can look at let's build some structure here. So we have the pair of numbers I and j. Then for time, I denotes the time steps. So time is I times delta t. I is 1 to whatever, n, right? So n time steps. So 1 times delta t, 2 times delta t, and so on and so forth. So that gives us the time dimension here. And j is for the interest rate dimension. So then a particular value of r is always whatever j, how many steps of delta j. Okay, so you start at 0. So you have 5 steps up, then it'll be 5 times delta J. So J is equal to 5 and 5 times delta R. So 1 times delta R, 2 times delta R, 3, 4, 5, and so on. And there's obviously variable I for time index is a positive integer, right? But J can be positive if it's this way, 0, which is unchanged, or negative, okay, it's going down. So, but they're all integers though. Now in the trinomial tree we build, we actually have 3 different types of tree branching. Unlike the binomial tree we saw before, it was just one type of branching out. Here we have 3 types. So if we denote this as the A type of branching, which means that the middle branch is the one that the rate will not change. And here is that it goes one, whatever the rate plus delta R up. And here is one delta R down, okay? But they're symmetric. This is unchanged, this is one up, this is one down. In branching B, you don't have a branch down. The lowest branch is actually unchanged. You have one branch that is 1 delta R up, and the other branch is 2 delta R up. And type C, you don't have any up movement. You have one unchanged movement, and you have one branch that is minus delta R, and this is minus 2 times delta R. Okay, and we have to determine, when we have this A branch, when we use type B branch, when do we use type C branch. And by doing that, we have to define some value called A max and A mean. A max is really some integer that is greater than this value. Okay, so you calculate this value, 0.184 divided by A times delta T. Depending on your delta T and depending on your A, you get this number. Okay, so if number is, say, 5.6, then J max is the smallest integer greater than 5.6, which will be 6. So when you have reaching to 6, you won't then have going down. You cannot go up anymore. So you will switch to type C, which is after that you will only go down. And J mean is minus J max. So in this case, if this thing is 5.6, J mean is minus 6. And then, so if you have 6 steps down already, 6 times delta R minus 6 times delta R, then you have to switch back to branch B, which means that you can only go up, cannot go down anymore. Okay, so if we're in between, you use this branch A here. Okay, let's see how this is implemented. So in the first step, then let's first match the first 2 moments, 2 moments of the distribution. So the mean change of this R star in time delta T is obviously this minus A times R star delta T. And this part is basically taken from here. So this is the drift, that's why it's the mean. Then the variance of change obviously is whatever the variance here is, this volatility sigma squared times delta T, okay? And you know, if you look at a particular node, your value of R star is depends on this, you know, your node J, Ij. So I is this way, J is this way. So if J number will tell you where you are, and you're really J times delta R star is what your R star value is. Now, you have a trinomial tree and you have 3 equations. You have to, however, match 2 moments. So you need a third condition. The third condition is really all the probability when they add it together must be equal to 1. So then you have 3 equations. Then you can determine 3 things, 3 variables. So here you look at the expected value. So probability up, probability medium, probability down. This is how much up will be. And this is the, if you're in the middle branch, what the change of your rate will be. This is the down branch, what is the change of your rate. Then this must match the mean change. And here you have the condition that matches the variance. Okay, so this is the expected square change, and here is basically is the variance times the square of the expected. Now we then should be able to calculate for, you know, under this generic condition that we need to calculate for each of the branch types. We have 3 types. So let's see for branch type A, where A here, the middle change here is no change. Okay, so because of this, we then only have 2 terms. So the PM times this delta R star M dropped out because this delta R star M is equal to 0. So this term dropped out, I want to have this 2. So that's give us the first equation there. And now you look at it actually in this one, compare this to this one here. We drop this, but here we also change the sign here. It's minus PD delta R star. And what is not plus? Well, we have to change the sign. It's because delta R is an absolute value, and here we're going down. So we have to minus this delta R, because the delta R is a negative number. Delta R is a negative number here. Delta RD. And here we only have delta R, which is the absolute magnitude. So delta RD is equal to minus delta R star. Okay, that's where we have the minus sign here. So that's equal to this. And here, because we're taking the square, so we have the plus sign here. Okay, so that's equal to this, which matches this part here. And given this condition here, now we can solve that. Okay, so we have actually, all right, so basically that's the answer for those ones, because this part is 0, this one is positive that we talked about. Okay, we will solve it later. For each one, let's talk about the equations, how we set up for each of the branch types. So for branch type B, you're looking at this. So the first one, you have the R, the delta R U in this case, the delta R star U in this case becomes 2 delta R star. So that times PU, because that goes 2 step up. And the middle one only go 1 step. And the third one is the change is 0. That's why it dropped out. And for this one here, same thing. You take the square and you try to match the variance here. You always have this condition. Now for type C, the first one get dropped out. The second one, the D one is 2 step down. The medium one is one step down. So minus only 1 delta R. Here is minus 2 delta R. That matches the mean. This matches the variance. You got this condition. So you can solve that for the probabilities. So for type branch A, depending on what A is, what J and delta T you have your probability of this, and this, PU, PM, and PD. And it's given by this equation here. You can just solve those equations that we've seen earlier. You will get this number here. And similarly, for branch B, you have a similar but different equation here. Okay. So for the first one, the sign here is different. So they're similar but different. Now you can also do the same thing for, actually there's a typo here. This shouldn't be type C. It shouldn't be type A, this should be type C. So for type C, you will have this probability being calculated. Okay. So that's illustrate with an example in the next video.